In this video, let's approximate or let's derive how many onto functions can be defined from set A to set B. So first off, we could introduce some notation like let M be the cardinality of A. Let's also introduce N to be the cardinality of B, our codomain. We have solved previously that the number of distinct functions from set A to set B will be the total is equals to your cardinality for the codomain raised to the domain cardinality, or using our new notation, that will be n raised to m. Thus, if we are going to solve how many onto functions are there, we could consider a large set. Say within this set there are elements that doesn't satisfy, so there are sets that don't satisfy the onto condition. Say the total cardinality of this particular set will be n raised to m is the total, and this part here is the number of onto functions. These are onto functions, and within this sets that doesn't satisfy the onto functions, we are simply going to subtract it from the total. But what are these functions that doesn't satisfy onto definition? Say, let's give them a name. Say this is set 1, C1, set C2, C3, and so on until C sub n, being the n the cardinality of set B, or the codomain elements. Which property does the set C have? So if we are going to have y sub I being an element of our codomain set B, this property, if the function is not onto, then this y sub I should not be included in the images of the function c sub I, or the functions within c sub I. So in this case, for example, c sub 1 does not include y sub 1, c sub 2 does not include y sub 2, c sub 3 are the group of functions that does not include y sub 3, and so on. So basically the problem will be a matter of computing the union of the C sets that again doesn't satisfy the definition of our onto functions, and subtracting them from the total to derive the onto number of onto functions. So more formally, we could express this as, say, let's subtract, use the subtract notation, the difference. So let's just have a total of surjective functions, so S for example, that can be expressed in terms of this total. So let me call this functions f, for example, or set f, total functions f. So that will be minus the cardinality or the union. So let's have the union of c sub i's from 1 up to n. So when we take the cardinality for that, and this term, so this whole equation, basically we could simplify this whole equation using inclusion exclusion principle. Basically the rationale behind that is, since some of these elements or these sets are not mutually exclusive, so that means they have intersection. So their intersection here, like for example, we will color green what is uniquely one element that is not included. Their intersection will involve two elements that are not included, and three elements, and so on, up to n elements that are not included. So that's n element is basically the intersection of all of these sets C when we do not include all of the elements. So this formula can be generalized with the general formula summation of, say, -1 raised to k. This is to take care of the sign because we're going to subtract some elements because they're counted twice. So n combination k and n minus k raised to m. So from k0 up to n. And we could expand this formula just for clarification. So where did the total elements went? So the total elements basically became the first element at 0. So when k is 0, we have -1 raised to 0, that will be 0, n combination taken 0, and then n minus 0, so this will be n raised to m. So for the first element, it will be first, when k equals 1, it will be subtracted because the k is an odd number, and -1 raised to an odd number will be subtraction or negative. So this will become n taken k 1, so n minus 1 raised to m, and so on. So this will be positive n combination 2, n minus 2 raised to m minus, and so on. So this is now the general formula for computing an onto function. This is special cases, of course, if m is less than the n. Okay, these are the cardinalities of a and b. So in this case, we cannot satisfy the onto principle if there are less elements for less domain elements, because if you remember, the definition for onto is all the codomain elements must be assigned, and we cannot do that if there are less domain elements than the codomain. There's also another, so in this case this is 0 onto functions. There's also a case when m is equals to n, and in this special case the result will be simply the n factorial or m factorial because they're equal anyway. So this general formula is generally applicable for when the domain elements is greater than or equal to n. Finally, for the last question, we have the how many bijective functions can be defined from set A to P. So again, if we observe the cardinality for A to be m and cardinality of B to be n, so if m is less than n, then we don't have onto functions, so 0 onto functions. Therefore, we cannot have bijective functions, so 0 bijective functions. The other case is when m is greater than n, in which case there will be 0 one-to-one functions. And therefore 0 bijection as well. Thus, for us to have a bijective functions, then it's required for m to be equal to n. And with that requirement, we can have n factorial onto functions, and at the same time we have n factorial one-to-one functions. And it follows n factorial bijective functions. And that is if the equality m equals n is satisfied. For the rest of the cases, well, we don't have any bijective functions. So that's it for the combinatorics.